My name is Prateek Sharma. I'm here to present our paper, SpotCheck, designing a derivative infrastructure as a service cloud on the spot market. This is joint work with Stephen Lee, Tian, David Irwin, and Prashant Shenoy. And we are all from UMass Amherst. As we all know, cloud computing has become very popular, and it offers many advantages to the users who deploy their applications on the cloud. It is relatively easy to deploy, manage, and scale your application, and users can simply pay as they go for the computing resources that their application needs, rather than all the hassle of maintaining your own hardware. Depending on what is offered as a service, there are many types of clouds, like infrastructure clouds, platform clouds, and software as a service clouds. In this talk, I'm going to focus on infrastructure clouds, like Amazon EC2, Microsoft Azure, and Google's cloud platform. These infrastructure clouds offer computing and storage resources to users on which they can run their unmodified applications. So the servers which are offered by these infrastructure cloud providers come in a variety of types, and each type has its own cost versus availability trade-off. The first type of servers are what are called as on-demand servers. On-demand servers have a fixed price per unit time, and once it has been allocated to the user, the cloud provider cannot intentionally or forcibly revoke these servers from the user. The other type of servers are what are called as spot servers. Spot servers have a variable price, which is dependent on the market conditions, such as supply and demand of the cloud servers in that market. An important point to note about these spot servers is that they are revocable, which means that the cloud provider can forcibly take the server away from you after it has been allocated to you. So you might be asking, why do spot servers even exist? So spot servers allow the cloud provider to sell off their surplus capacity. So if a server is idle during periods of low demand or during off-peak periods, these idle servers can be sold off at very low costs. This graph shows the price difference in the on-demand server and this average spot price of two kinds of servers on the EC2 spot market. We have seen that on average, spot servers are between 2 to 10 times cheaper than their equivalent on-demand instances. So what can these spot servers be used for? Conventionally, spot servers have found great use in batch applications. So for example, if you want to run your data processing tasks or analytics or some scientific computing jobs, then these jobs are the perfect kind of jobs for spot servers, because batch jobs are generally disruption tolerant and have built-in mechanisms like checkpoint restart, which enable them to tolerate these volatile spot servers. Now we can ask the question, can we use spot servers to run some other kind of applications? So let's say you want to run the software stack for an online store. Can you possibly run this entire stack on a spot server? Well, the problem is that since spot servers are revocable, and if a spot server gets revoked, then your application has nowhere to run and will face a downtime. But can we do something about this? Can we somehow mitigate the effect of this revocation so that we can run any application at drastically lower costs? So let us look at one naive solution. You run your application on the spot server. When the spot server gets revoked, you simply migrate your application to an on-demand server. Now note that an on-demand server is non-revocable. There are a few drawbacks with this naive solution. As you've just heard, migration can send a lot of data and it takes a long time to complete. If a migration doesn't complete before the server is terminated, that may result in a loss of application state. Another scenario can be that the application may not natively support migration. So this means that this migration, which is triggered by the revocation, imposes an inherent risk. And since users want to do all their computation in a hassle-free manner, we cannot really expect the users to manage all this complexity and risk associated with the migration. So in the rest of this talk, I'm going to address these drawbacks and show you the design of our system, which can use transparently a mix of spot and on-demand servers to run any application at very low costs. Having provided the motivation, I'm going to talk about our system design and present a few of the experimental results. I'm going to end with the related work followed by the concluding remarks. To best describe our system, we use this notion of a derivative cloud, which is an intermediate layer sitting between the native cloud and the user. A derivative cloud is kind of like a cloud broker. It buys or leases servers from the infrastructure cloud provider and then resells these servers to the users. The servers which are offered by the derivative cloud can come with different SLA and different costs than what is actually provided by the native cloud. An important notion in a derivative cloud is that of a server pool, which is simply a collection of servers of one type. So by combining different server pools, a derivative cloud can create new abstractions of servers and offer them to users. Note that these servers may not actually exist. For example, we can combine the spot pool and the on-demand pool to present a new type of server which has the low cost of the spot servers and the non-revocable nature of the on-demand servers. We have actually built such a system and we call it SpotCheck. SpotCheck is a derivative cloud built on top of Amazon EC2 and it uses a combination of spot and on-demand servers. It is able to provide low-cost, non-revocable instances on which users can run their unmodified applications. The key idea behind SpotCheck is to run applications on the spot server whenever we can, and when the spot servers are revoked, you migrate them to an on-demand server. An essential requirement for this key idea to work is that we need some ability to transparently migrate VMs without losing any state, which means that the migration has to occur in a safe manner. So how can we do this migration? A naive approach would be to use virtual machine live migration. But live migration requires a long time to complete depending on the memory size of the VM or the application characteristics running inside the VM. Luckily, there is a small termination warning provided by Amazon, which is of about 2 minutes. So which means that we have 2 minutes to migrate our VM. But if we don't succeed in doing so, this may result in loss of VM state. So how do we solve this problem? We use a technique called bounded time VM live migration, which ensures that the VM can migrate from one server to another in a guaranteed pre-specified bounded time. Unlike live migration, this is independent of the VM memory size or the application characteristics. The way it works is a bit like live migration, but it continuously checkpoints VM memory to a disk on the backup server. It can migrate the VM in bounded time by ensuring that the residual dirty pages are always kept under a limit such that all of the residual state can be transferred to the backup server when the spot instance termination warning is received. The backup server runs on a separate dedicated on-demand server and can support multiple VMs. When it is time to resume on an on-demand server, we employ an optimization which we call lazy restore, which simply means that we can restore the VM as soon as possible without restoring all the memory pages. This works by simply fetching pages of the VM from the backup server as they are being accessed on the on-demand server. So bounded time VM migration is great, but this, just like VM live migration, is a virtualization mechanism which requires hypervisor support. And as far as we are aware, no popular cloud provider will allow these migration mechanisms to be exposed to the user, nor do they allow us to modify the hypervisor for security and other reasons. The way we tackle this problem is by using nested virtualization. We run our own hypervisor, XenBlanket, on top of the cloud server provided to us, and then we run the user VM inside this nested hypervisor. We have modified XenBlanket to include our bounded time live migration mechanism. Great. So migrating is nice, but it would be even nicer to not have to migrate at all. A problem that arises with Spot servers is that of revocation storm. If the market prices increases, this means that all the Spot servers can potentially go away. So we have this problem of this storm when all the VMs have to eventually be migrated to an on-demand server in quick succession. So how do we solve this problem? Well, we have a very simple solution of using multiple independent Spot pools such that the revocations in one Spot pool do not affect the revocations in the other Spot pools. To simplify, we don't put all our eggs in one basket and we try to distribute VMs on as many independent pools as possible. So what are these different Spot pools? We have observed that different availability zones and servers of different sizes have uncorrelated Spot prices, which means that their failures are also uncorrelated. As a result, we can employ multiple simple policies to distribute user VMs to different Spot pools. For example, we can do it equally, or we can do it by a weighted ratio of the server pool costs or by a weighted ratio of the server pool availability. Doing all this is a centralized controller which sits on a dedicated instance which can dynamically do all this mapping for new user VMs. Great. So having described some aspects of our design, now I'm going to move to the evaluation. As mentioned earlier, we have prototyped SpotCheck on Amazon EC2, and I'm going to describe the application performance, the cost, and the availability of SpotCheck VMs. These results are going to be shown using the SpecGBB and the TPCW benchmarks. We have run all our experiments on the EC2 M3 medium instance, and we have used real price traces over a 6-month period from last year. So let us look at performance. The first thing we want to know is what is the performance impact of the continuous checkpointing required for the bounded time migration. We observe that this is heavily dependent on the application. For example, for SpecGBB, it is more or less negligible, whereas for TPCW, which is highly interactive, it can go up to around 17%, which is noticeable but tolerable. The next question we want to answer is how many VMs can be run on a single backup server, because the backup server is the extra cost of our system. In general, we can run many tens of VMs on a single, which all back up to a single backup server. For SpecGBB, for instance, we can run up to around 40 VMs without seeing a big drop in application performance. This means that we can run 40 VMs on a backup server, and each VM only pays 1/40th this additional cost of the backup server. This graph shows what is the actual average cost of SpotCheck VMs. So we evaluated the different pool management policies which I talked about earlier, starting with a simple one pool policy, moving on to as complicated as 4 different Spot pools. We see that the average cost in all cases is about the same, and that comes to around 1.4 cents an hour for the M3 medium instance. This results in a cost saving of 80% as compared to the equivalent on-demand server. Note that with live migration, which does not require the backup server, but can only migrate small VMs and of certain application type, the cost is much lower, is slightly lower because you don't have to pay the extra cost of the backup server. Next, we are interested in how available SpotCheck VMs are. Here we compare the 2 VM restoration mechanisms, the full restore, which fully restores VM memory and then starts executing it, and then our optimized lazy restore, which can restore VM and fetch pages on demand. With full restore, we get an unavailability of around 0.02% for the one pool scenario and 0.16% for the 4 pool scenario. This is a range of 3 nines to 4 nines of availability. With lazy restore, we get much better results. we get from around 4 nines to 5 nines of availability with respect to the native on-demand servers of the cloud. The downtime with lazy restore is mainly caused by the migrations, and the culprit here is the latency of the native cloud operations for detaching and attaching network and storage interfaces. So having described our system, it's time to move on to related work. This work has been possible only because of the large amount of work done previously in this area. A lot of work has been done in spot instances and spot pricing and bidding. This is only some of the work. So this notion of derivative clouds is new, but similar systems like PyCloud and Heroku implement a version of derivative clouds. We heavily use nested virtualization, and nested hardware virtualization was pioneered by the Turtles project, and we heavily use and modify Zen Blanket. The Bowden type migration is based on our previous work, Yank, which in turn was based on Remus. And the lazy VM restoration is very similar to post-copy live migration and Snowflock. So in this talk, I talked about the different kind of servers in public clouds, and a very interesting type of server called spot servers, which are very cheap, but they are volatile. I talked about SpotCheck, which is our derivative cloud on the spot market, which gives users low cost and high availability. With that, I thank you and would like to answer any questions.
Thank you for the talk. I just have a small question. How much of the result can hold if the cost model changes, or the whole business model changes, or yeah?
Yeah, I think that's a great question. So all the cost results are certainly dependent on what the underlying spot prices are. We have seen that overall they are quite stable, but they may change. Okay, to better answer the question, this is what the expected cost kind of looks like, and the only component that would change is what the probability of the revocations is and what is the average spot price. So, yeah.
Thank you.
Hi.
Yes.
Hi, Jacob Hansen, Bromium. Very cool work. So I think this would get really interesting if you could migrate to another cloud and get another spot VM over there. Mm-hmm. Have you thought about that?
That's a great idea, but there are a few practical challenges. For instance, network latency, which is and we send a lot of traffic from the VMs to the backup server, so that would add to the cost as well as the performance. And of course, we need a unified way of storing and accessing network interfaces and managing them. So there are a few practical limitations to that approach.
Yeah, thanks.
Hi, Bill Bolosky from MSR. Two questions. First, the computation that you did for the amount of backup servers, you used the spec JBB that seemed to have a fairly low page dirtying rate based on the previous number. If you used TPCW, your one that was presumably dirtying memory higher, how much of a backup server would that take?
So in fact, spec JBB dirties memory at a higher rate than TPCW. Okay. So even for TPCW, the graph is in the paper, but you can easily run at least 40 VMs all running TPCW on a single backup server.
Okay. Yeah. So second question was actually related to the earlier one, which is that it seems to me that one effect of this might be that you've effectively increased the value of a spot instance because it, right? And so economic theory kind of says if you've done that, then the price is going to go up too.
Sure.
And so it might be that what comes out of this is you wind up causing the spot market to have more demand, mm-hmm. and so the savings goes away once other people. I mean, it's great if you're the only one who has it.
Right.
But
right.
I don't know that you.
So I think that's a question which we battle with quite a lot. But like in the end, we can't predict second-order effects or how the market is going to react. And we think that the spot market is large enough to sort of withstand such a system. And there is additional incentive for the cloud providers to sort of expand their spot markets because of the whole, it makes it more efficient for them since bidding is kind of truth revealing as to what users actually need.
Right.
So,
I think the spot market mostly comes from reserve capacity that they have to make their system run.
yes,
They make more money from selling on-demand instances. They would rather sell those to you than spot instances. They sell the spot
Sure.
instances because it's free to them,
sure.
right?
Yeah.
So my guess is that your system would actually benefit Amazon more than your users, because they'd make more money because the prices would go up. But anyway.
It's possible, yeah. Thanks.
Hi, Cheng Tan from NYU, New York University. Hi, here.
Sorry.
Hi,
Okay,
I have a question about your backup system. So is it the same as a code migration, which means you just take snapshot and then restore in another, physical machine? My question is, what's the difference between your backup mechanism and very original, just a snapshot and then restore another? Yeah.
Okay, so the difference is that our mechanism is live. It has no downtime. We don't stop the VM and then take a snapshot.
Okay, so here has another question is, as far as spot VM, that spot machine will trying to gone, here the most priority one is the correctness of the VM rather than the liveness, right? So if we use just the code migration, it will take maybe several seconds. But I think because this is not frequent happens, so I think, do you think
So-
this is another approach for a question? Thank you.
I think that even that would depend on the size of the memory of the VM. Like for really large memory sizes, you would not be able to completely do the snapshotting in the 2 minutes.
I'm not sure the spot machine will gone in how long a time?
Oh, that's true. So the probability of revocation is quite low, but we still would like to have as low downtime for applications as possible.
Okay, I see. Thank you.